The companies that spent the last 2 decades building asset-light software empires are now morphing into debt-reliant heavy industries. By 2026, the four largest cloud hyperscalers are on track to spend $725 billion on artificial intelligence infrastructure. That acceleration represents a massive jump from the roughly $410 billion projected for 2025. This chart illustrates the pressure. Operating cash flow grows steadily, but capital expenditure accelerates at 70%. In Q3 2026, they cross. Infrastructure costs overtake cash generation. Consequently, free cash flow collapses from $45 billion to just $4 billion. When a business generates record cash from operations, but has almost nothing left after paying for capital infrastructure, the model has shifted. The most efficient cash-generating machines in history are now burning through their reserves simply to pay the rising entry fee of the AI race. You can see exactly what happens when physical infrastructure costs outpace cash generation by looking at Oracle's balance sheet. The company has verifiable demand for its compute power. In its fiscal 2026 results, Oracle reported remaining performance obligations reaching $638 billion. Fulfilling that demand requires steel, power, and chips. Oracle's capital expenditure rose to $55.7 billion, driving their free cash flow to a negative $23.7 billion. To sustain the physical build-out, Oracle announced it expects to raise approximately $40 billion through debt and equity financing in fiscal 2027. The immediate market reaction to this structural shift was severe, with Oracle stock dropping nearly 20% in a single week as investors absorbed the new math. Compute demand is entirely real, but the massive upfront cost of the physical infrastructure breaks the traditional software balance sheet. The AI build-out has officially migrated from tech sector earnings calls into the global credit markets. The direct catalyst is a structural shift in how artificial intelligence actually operates. The industry is moving from episodic chatbots to continuous agentic systems. The first generation of AI relied on episodic inference. A user types a prompt, the system generates an answer, and it creates a single temporary spike in compute demand. Agentic AI relies on persistent inference. These systems operate continuously, executing complex workflows without human prompts. That continuous operation demands a massive increase in raw processing power. Multi-agent systems utilize approximately 15 times more computational tokens. They are also designed to run perpetually. Instead of brief bursts of activity, these agents maintain persistent operation 24 hours a day. When you multiply that increased token usage by continuous operation, the true cost emerges. Agentic tools are 60 to 130 times more energy-intensive than the chatbots that preceded them. The legacy data centers currently powering the internet simply cannot support this. They are mathematically obsolete against a continuous, high-density workload of this magnitude. Scaling this new architecture requires looking past corporate finance and examining macroeconomic physical infrastructure. The national power grid's capacity to deliver high-density electricity now serves as the absolute ceiling of AI expansion. This chart reveals an impending supply failure. The U.S. faces a 45 gigawatt power shortfall for data centers by 2028. Bridging that gap requires heavy reliance on gas turbines and peaker plants over renewables. By 2030, we will need 72 gigawatts of entirely new power capacity. To put 72 gigawatts into perspective, that is equivalent to the total energy output of 72 large-scale nuclear power plants. The primary limit on artificial intelligence is no longer algorithmic efficiency in a research lab. It is the brute force availability of electricity on the physical grid. That massive energy deficit is just the first domino. It triggers a cascading series of choke points across the entire physical supply chain. Securing critical high-voltage grid components, like industrial substations and specialized cables, now requires navigating severe logistical hurdles and years-long wait times. Then there is the human capital constraint. Expanding the grid demands a highly specialized, non-scalable workforce. The U.S. will need over 207,000 skilled transmission and distribution workers to build this infrastructure. Each role requires years of specialized training. These physical constraints have severe downstream consequences for software startups. As hyperscalers absorb the costs of this infrastructure squeeze, they will pass the bill on to developers. To protect their own shrinking margins, cloud providers will likely raise the price of compute access, or simply bundle the most profitable application layers directly into their own native products. The global AI race has evolved past the software layer. It's now a physical contest for heavy industrial steel, vast raw land, and skilled human labor. There is a stark disparity between where the market is currently concentrating its capital and where the physical bottlenecks dictate that capital actually needs to go. This diagram shows current AI profit pools, revealing how the market treats upstream hardware manufacturing as the core. Upstream assets like chips, memory, and manufacturing capture 90%. Meanwhile, downstream infrastructure enablers, building power systems, components, and services, capture only a tiny fraction. The combined earnings of upstream hardware providers is nearly 9 times higher than the physical enablers required to keep those chips running. The physical components that ultimately dictate the speed and scale of global AI deployment currently capture just 10% of its financial value. To physically sustain the rollout of continuous agentic AI, immense capital must aggressively migrate downstream to these physical infrastructure enablers. That means funding grid-connected generation, distributed behind-the-meter energy solutions, and advanced thermal backup systems. It requires investing in the critical hardware providers positioned directly at supply chain choke points, specifically those manufacturing advanced power distribution equipment. It demands specialized mission-critical services, ranging from end-to-end design engineering to highly technical data center fiber splicing. And finally, it requires high-performance data centers located in established urban grids, engineered specifically to handle continuous, persistent workloads. Solving the physical choke points required to power these models will define the ultimate financial winners of the AI 2.0 era.